Okay, welcome all. So before starting this session, please let me know, am I audible? Can anybody write yes? Am I audible? Am I audible? Okay, thank you very much. I got the responses. So welcome to the lecture 4, session 1, and we are going to discuss very important things today. And in the last class, we were actually talking about that when we are going to develop a artificial intelligence based system. So for such a system, how we can specify that, how we can formally specify the problem, and then how we can find out a solution. And the first step was to define the problem, and we have seen that to formulate a artificial intelligence problem, it is better to have these 5 important things. And one of them actually tells you that means you need to first define that what are the states, and then you have to tell that this particular state is an initial state. So for example, we were discussing about a problem where we have a city map of a city, and the agent wanted to move from one location to the another location. So in those scenarios, we can say that the places are actually the nodes, and initial state could be the place where the agent is starting. Then we can define what are the actions he can take. Means he can go from one place to another, and etc. So most of the times, for example, in this case, these set of actions would not be a very large set. It would be a reasonably small set, and then we want to see that what is the transaction, how the system is going to do a transaction. So transaction means if you specify 2 things, number 1, what is your state and what action you are going to take, then the systems you should be able to tell that what is the next state. So how you can store all these things into the computer? So one way that you write down all the states, and for every state, since on the every state you can take the action, you write down what actions can be taken on these in this state, and then you specify that what is going to be the next state. So this is a model where you can say I can create a table to express the transaction table. But sometimes you see that there are 2 issues. Number 1, that in some of the states it may be possible that all the actions cannot be taken. Few only specific actions could be taken. And similarly, you can also have an issue that if a lot of states you have, either your system is contain lot of states, then you somehow need to reduce this space, and that you can do by devising a function that can directly take and somehow can predict the things. Then you would be telling a special function that is called the goal test, that tells that whether a particular state is a goal state or not. So whenever you are taking a transaction, you test that whether that state is goal or not. If you are into the goal state, you are done. Then there is a notion of efficiency that tells that even if you are doing the things, how good you are. And to go ahead with that thing, notion of efficiency, we need path cost, means what is the cost that when you reached over there. So we want to minimize the cost. This is very important thing. So we have in the last class we have seen a goal-based agent, and we call it the problem-solving agent. And we have discussed in the even previous class that there could be a reflex agent, means just seeing the things he performs some operation. And and we have highlighted that such a system is very important because they immediately take the decision, and sometimes it is required. For example, our system also has some reflex actions. For example, if you see some explosion happening, then by yourself you could stand up. Some fly is striking at your eyes, so your eyes will by automatically get closed. So this is all the reflex actions, means you need not to think about them, because if you start thinking that this is happening, what to do, so brain would take more time and you would not be able to in a position to take the things. So reflex actions are also important, but those cannot be used as a big system when your system is big, because they cannot do a planning kind of thing. They can only do the things at a particular moment. So therefore, we have discussed in the last class that if you want to make a system, so you have to define some goal, and your system should be a goal-based system, and such a system would be called we are going to call as a problem-solving agent. And we have also discussed in the last class that when you are when you are telling about the state of the system, you should state it very abstract level. Because if you are going at the very much detail that is not required, then there would be a lot of uncertainty in defining the thing, and therefore you would not be able to define the thing. For example, if I say that your state your state is you are on a road, and your state could be at the 1 kilometer, at the 2 kilometer, at the 3 kilometer, 4 kilometer. Let's assume that there is a road between city A and B, and it is a 10 kilometer long. So I can define your state as whether you are before 1 kilometer, whether you are before 2 kilometer, whether you are before 3 kilometer, 5 kilometer, 10 kilometer. Then by this I can define the states. But if I define the state more concretely, that what is your direction in which you are, what is the direction of steering, what is the place in which you are sitting, then there is a lot of uncertainty, and the number of states are actually increasing exponentially, and then you would not be able to represent and solve the particular problem. So this is very important, that whenever you are going to define tell a goal-based system, you should also do a abstraction on the states, so that number of states are limited. In the last class, we have discussed some of the problems that, and we have seen that how we can formulate and specify about these 5 things. And one of them was a vacuum cleaner. Toy vacuum cleaner example, where we have seen that there were only 2 rooms are there and it have to clean, and we have seen that all the state space we have drawn in the last class. We have also seen an example of 8 puzzle, where into the 3x3 grid there is one is hole, and that hole can propagate anywhere, and by this numbers are actually getting changed. Node conjecture, route finding, towering problem, traveling salesman problem, and the VLSI layout, robot navigation, automatic assembly sequencing. So a lot of these things we have discussed in the last class. And then we have also discussed these 2 approaches for solving these things, and it was a depth first search and breadth first search. So before going forward, I just want to tell you this understanding, that please understand this very important concept, that if you, I don't know what happened here, that number one thing, I think is it very much, why it is happening, why there is a grid. Okay, so let me just draw. Okay, the grid is not important. Okay, so I want to tell you one thing, that there are 2 views. Number one is environment, and one is that is being represented into the system. Okay, so sometime when the system is not told about all the states into the environment, let's assume that there are 1, 2, 3, 4, 5, 6 states. So it may, and we somehow define that if you take this action, you reach to this state and you reach to this space. Kind of, there is an automata that can fully describe. So it may be possible, what I want to tell, that it may be possible that your system learns something different. Means it may not have these 6 states, it may have only 4 states, and using those 4 states and their transaction, it can define the things which are there. Why it can happen? Why it can happen? It can happen because of 2 reasons. Number one, all the interactions with the environment are not shown to the system, because they may be infinite interactions. So whatever information is shown to the system, your system has built around that only. So it may get an understanding, so that whatever I have seen to explain those things, this particular model is best. But that may not be the actual environment, and that is the reason for the most of the cases when we have a misclassification, because when a new example comes, new condition comes, so your system don't understand that. But whatever example is shown to you, for that your system is good. So okay, so this is a very important point. So we have seen one more thing, that if you define all the states, if you define all this relationship, then finding the solution means I want to go from this state to this state. Your answer would be that take these steps, so that you can go ahead to the solution. Okay, am I clear? So on the higher level, just understand that whatever the system is understanding, let's assume the system is understanding this particular model, that there are some states. Let's assume that this is a state, this is a state, this is a state. These are states, and there is some relationship. You go from here to here, here to here, taking some action. Let's assume that green is an action that you are going to take, and there are some blue actions that you can take. If you take the blue action on this, you go to this. So there are green and blue action. Let's assume, oh, I have drawn on the same place too. No issues. So you can say that these are the things that are going to happen. Let's assume. So if I say you that you are into this state, I say that this is the initial state. So I represent like this. I say that you are into this state and you want to come into this state. You finally want to come into this state. Okay. So this is the goal state. Okay. Goal state, and this is the initial state, start state. So what is your answer? How would you tell that? How can you reach to this state? So for example, into this case, you can see that you cannot reach it to this place because this is an isolated node, and whatever action, because I think I have not given the action. Let's assume that I give this link. So do we have a path? Do we have a path? So I have just created one, that you from this place you come to this particular node, and then from this node you go to this node. So this is what your answer is. Okay. So how can you come to this answer? You the only thing you have to do is to you go to this state. Let I call it as state 1, state 2, state 3, state 4, state 5, state 6, state 7, state 8, and state 9. If I say like this, so you start from S1 and then you say that you can go to the S4. If there was one more, say S4 and S3, let's assume that this was also possible. So you say that I would go to the S4 and S3, and then you have to find out that what you can do from here. From S4 you can go to the S8 and S7. So this is what the tree is, and from 3 you can go S4. Sorry, I think it should be S6, and I think this is the only place, and S7 also. Okay. So there are two paths available. Okay. So to go to this path, for example, here you can see that you have two paths available. The one is this path, and the another is this path. So number one thing, that either if we are only satisfied by seeing your answer, if I'm only concerned that give me the answer, so this would be a right answer. You would say that S1 go to S4, then S4 you go to S7. This is what your answer is. Okay, but if I'm concerned about the how good I am, then somebody have, let's assume, given some number also. So I'm not going to into the detail over here. I just want to figure this out, explain this thing, that you have to find out this kind of relationship that tells you that from S1 you go to the S4, and S4 you go to the S7 by taking whatever action you specify, that you take this action and this action. Okay, so this is your answer is. So how can you reach to this thing? The answer is you go to S1, you explore all possibilities, and then out of them you go explore the another one. Then from S4 you explain all the possibilities and try to see what is other possible. What are the other possibilities? If you find S7 over there, you are done. So this is called the exploration. So every step you start from here and you do the exploration, and this is called the search. This exploration is technically called search into the AI community. So here this is what the search is. Okay, so we can apply two kind of search strategies. One is depth first search and another is a best first search. So we have seen in this in the last class that what is DFS and BFS. Okay, so hope you understand this. So there are various such strategies possible. Out of them, two we have seen in the last class. But you can classify, you can categorize both the various searching strategies into two categories. One is the uninformed search, or we call it blind search also, and another is the informed search, and which is also called the heuristic search. So there could be two categories of the search algorithms. One is the blind search algorithm, another is the heuristic search algorithm. The BFS and DFS, both the algorithm that we have studied, falls into the category of uninformed or the blind search strategy. So we would also be seeing other research strategies and in this class. So we have seen in the last class that two algorithms we have seen. Other algorithms we would be seeing into this class, and we would be also seeing some heuristic search techniques. Okay. So what is the difference between the blind search and the heuristic search or informed search? The difference is that into the uninformed search, the system or the search algorithm is only provided by the problem definition. Means what is the problem definition and what are the states? Only these information is provided. So whatever information is provided is there into the question. Only that information is available. No extra information is available. And here into the heuristic search thing, there is some extra information there. There is some extra information available. Okay, so what this extra from where this information comes, I'm not talking about. That is a different part we would be discussing later. But today we are not discussing that from where this extra information comes. But only our focus today is that into the informed search categories there is some there is some extra information, and that information can be used to find out that if you are into the state, some states say as question mark, and there are some other states say S1, S2, S3, S4. So you can compare two states. You can say that going S2 as compared to S3 is better. So you can say that I would not go to the S3 first. I would first go to the S2. So you can find out these kind of strategies if some extra information is available to you. But if no extra information is available, then what would you do? Because ultimately, if you are into this state and you have explored that there are 4 new states available, then in which state you are going to test next after X question mark? You may test S1, you may test S2, you may test S3, you may test S4. All these things comes by some procedures, and these procedure could be DFS. DFS says that says that you put all these things into stack. Okay, you put all these things into stack. Whenever when you are exploring all these things one by one, whatever the state is coming to you, you put them into stack. DFS says you put all these things one by one into queue. Okay, and then you initially from the question mark you got all these things, you put them into stock and queue, and after that you pick the things from the stack or queue. And the general name for all these things is a frontier. So we say that whenever I am into this state, I explore all other states and put all those new states into the frontier, and then I would go to take the new frontier, and I would take that item and perform the operations again. And what is the operation? What is the typical operation? So typical operation is this, that you have some system where there are a lot of states, S1 dot 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 Sx, X number of states you have, and you have lot of states, and what you are doing. Okay, so you are into the state S1, and you apply something to go to the next state. 1 minute. Okay, so what I wanted to say, that let's assume that you have S1 to X number of states, and you are into some state. Okay, initially you have a frontier. Frontier is actually nil, no item is there. Initially there is no item, but when you start, you put the first state, that is specified, that from the initial state you put the initial state into the frontier, and your algorithm does, number one, take something out of frontier. Okay, so what would happen? This would delete this item, and then you process. process it. And what the processing means? Processing means that test is it goal test. If it is goal, then you say that okay, I am done. If not, explore all descendants and put in frontier. Put in frontier until you repeat this process until frontier is empty. Is not empty. If the frontier is empty, you would stop. So what happened that when you took out the S1, what happened? You tested and you find out no, it's not the final state. Okay. Then you explore all the its neighbors. Then you say that S2, S3, S4, S5 they are put into the frontier, and then again you do the same thing. Means you have took out the S2, taken out the S2, and its neighbors are actually put into the frontier. Sometimes you also maintain an information that could be a color for all the nodes, saying color could be white, color could be gray, and color could be black. Color is initially white for all the item, but when the item is put into the frontier, its color becomes gray, and when it is taken out from the frontier, its color becomes black. Okay. There is a question, sir. Please tell if we will stop when the state is the goal state, apart from the frontier is empty. Yes, I told you na. The test is if goal. If I would be testing the thing, if it is I told it here that test if it is goal state. If it is a goal state, if yes, then you would exit and tell whatever the items you have taken out from the frontier. You would create a path and you give that path as a output, because you have explored all the path one by one. What is the logical path from you may be doing the backtracking to give the path. So you would exit, report path, and report path, how you can go from here to here, and you would exit. So these are the things. So I think that is pretty straightforward, and for the people like you who are coming from the industry, they are coding these things day and night, and it is, I think, your cup of tea. You know it better. Okay, so what I want to tell over here more. So I want to focus here that we have seen that what is the BFS, breadth first search, in the last class. That okay, let me go to the here again. Let me just take it. Let me take 5 and go here and put it here. Okay. So we were talking about DFS and BFS. Okay. This thing, what is the strategy of DFS and BFS? Can anybody tell? Let's talk about the breadth first search. Okay. So let's assume that you start from this S1 node, and then there is S2, and then there is S3, then there is S4, and then there is S5, S5, S6, S7, S8, and S9, and S10. Okay. So if I apply BFS, what is going to happen? Okay, if I apply BFS, so initially you would go to S1, and then you would go to the things which are nearby the S1. Which are the nearby S1? S4, S3, then S3, and then S2. And then you would go the nearby places are the nearby, because S3, S5, S4 has came to you, na? It would put S5 and S6. So you go S5, then you go S6, and then from the S3 you got S7 and S8, and then you from S2 you have inducted S9 and S10. Okay, and since I have not plot any members of these items, so therefore now your frontier would be empty. Otherwise, you would be getting those items. So this is what the sequence is. In the DFS, whereas into the Where into the depth first search, what is going to happen? You go for the depth. Initially, you come from here, you go here, then you go here, then you come back, then you go here, so that it is completely filled. Then you go here, then you go here, then here, then you go here, then you come back and you go here. So what is the sequence? The sequence is S4, S1, then S4, then S5, then S6, then S3, then S7, then S8, S8, then S2, then S9, and S10. This is what the sequence is. So let us see that two important thing. What are the two important things? That if you are into this state, let's assume you are into this state, what is the branching factor? How many next items are there? Although it is not a static thing, there could be things changing. So let's see. Let's fix something that let's say that let's assume that the branching factor, how many new items are given, is B. We represent is B. B as a branching factor. So let's assume that B item, maximum number of items that are B over here. And then we see that since these items are also branching, every item is branching. Okay. So how deep we can go? So let's assume this is the level 1. Okay. Let's assume that this is the level 1. This is the level. This is the level 2. This is level 3. Level 4. So how deep we can go? So let's assume that we can go to deep D. So this is the 0th level, 1 level, 2 level, like this. You can say that. Let's deep you can go. So how in every step the BFS generate, because in the frontier, if you are whenever you are starting, so if into the first line, how many things are included into the frontier? They are B things included. Okay. And when all these things are actually traversed, because one by one they came at the same time. So one by one, when you are evaluating them, exploring them, they again be indexing B items. So all B items would include B item, introduce B more items. So B. So if when you go into the level 3, again one more B component would be there. You go into the next level, again B would be there. B number of new item would be introduced to you. So in overall, how many item is introduced to you? B to the power D number of items. So this is what is written over here. So you get B to the power D number of items. That is also important over here to know that the breadth first search generate order of B to the power D nodes for evaluation. Okay. So same number of nodes is also generated into DFS, because let's assume those items are there. So for every item would be generated, so DFS would also be generating all those items. It would be generating the same item. But we know that the order is going to be different. Okay. Okay. So whenever we are going to design a strategy, either it is a uniform, uninformed, or the informed search, or blind search, or the heuristic search, we always have to cautious about what is the memory requirement and how much time it is going to take into the giving me the answer. Okay. So this we have done in the last class. I think this part has been not done in the last class, but this is also an important example. In the last class, we have seen that our model has have to actually travel from the place that is called Arad to this Bucharest. So from this place to this place, my agent have to move. Then what should be the right place? This was the question asked from him. Okay. So this map, why I am going to bring in front of you, so that you can take a print screen of this thing, because at the later point of time we would be talking various number of times over here. So please take a print screen, so that at the later point of time you can refer it. There is a question that how stock and queue will make the difference into the logic. Okay, there is a question that how stock and queue will make difference into the logic. So let me tell you that stock and queue, actually this is a very basic question. Just see that what is going to happen. I'm just going to give a very crude example. Okay, let's assume that you are going to put 1, 2, 3, 4, 5 and taking out these number. Okay, just and taking out this number from the stack. So stack is stock. Let us just call here stack, STSEK. How the stack works? That you put the first number, you put it over here. You got the second number, you put it here. You got the third number, you put it here. You got the fourth number, you put it here. You got the fifth number, you put it here. Now I'm going to ask you that give me the number. So how would you give? You would take out the first number and give me the 5, and then you would this number gone. Then you would give me 4, then you would give me 3, then you would give me 2, and then you would be giving me 1. This is how the stock is working. But if it is a queue, okay, the queue works like this. That it's a queue. Okay, so one by one item is going. So there are two places. This is the front. This is the rear. So item is inserted at the rear. So when the 1 came, you put it here. When the 2 came, you put it here. 3 came, you put it here. 4 came, you put it here. 5 came, you put it here. When I told you that give me the item, you would take the item from here and give that to me, and give that to me. You take it and give me 1. Okay. I ask second one. You remove it. Give me 2. You remove this 3. You remove this 4. You remove this 5. You see, na, the item which are coming out from the stack and queue are different. So is it clear? Okay, is it clear, Mira? Stack and queue, the made difference. Okay, thank you. So this graph, you please take the print screen, so because we'll be later time talking many of the time. So uninformed search. So we are going to talk about the more algorithm today. So next algorithm is the uniform cost search. Next algorithm is uniform cost search. What is the uniform cost search? This algorithm, the concept is this: let's not use the stock or queues as a frontier. So earlier we were using stack and queues. Whatever the output was, I was going by that thing. But now I am going to say that you don't use stack and queue. Instead, use a list that is sorted by using the path cost function, and we are going to tell it the GN, where n is the node in the list. Okay, where n is the nodes in the list. What do I mean? I mean this, that earlier what we were doing, whenever a new item was coming to me, I am sending it to the frontier. And into the and behind the curtains, what was there? Either stack or queue was there. Okay, queue was there. But I am going to tell this time that you use here a sorted array. Now you are going to use a sorted array. Sorting based on what? The path that I have traveled till now. Okay, the path that I have traveled till now. So what is going to happen? Let's assume that you have the state S1, S2, S3, and S4 over here, over here, and new state you get. Okay, that has, say, S5 comes, and that has the distance from the root node to this particular node is, say, 5. This node is, say, 10. This node may be 12. This node may be 18. This node may be 35. Okay, these things are actually into the increasing order. So let's assume S5 comes. So S5 would not go at the end. Neither it would go at the end, neither it would go into the forward, it would go into the right position. So you see that the S5 would be inserted over here. So next item would be S1. After S2, after S3, before S3 there would be S5 that would come out. Okay, so this is what I want to tell, that the algorithm tells this thing, that uniform cost search, and in the uniform cost search, what it does, that if the frontier is empty, you know that this algorithm you try to see that if initially whatever node is given, problem is given to you, you find out the node, what are the nodes, and then you initial state you put it as a state, and path cost is 0 because you are reaching to the goal state without any expense. So you put it here. Frontier should be a priority queue, and initially you put the only the state, the initial state over there. And explode, nothing is explode. Okay, so if empty, frontier is empty, means you don't have any items. Okay, So then you exit failure, means your item for which you are searching is not found. Otherwise, you pop from the frontier, you take out the first item, and you know the first item is the initial state. And if you test whether it is a goal state or not, if it is a goal state, you give me the solution. Okay, you return it as a solution, and otherwise you explore it. And for each of the items which are actually, this is very important thing, for each of the actions, because you are into this state, you apply all the actions and see what next can happen. And because as I told you that what is the exploration part, that whenever you are into a state, you see that what all actions can be taken and in which state you are going to be. And you see that if you are going to be into this state, so already if you have spent some X amount of rupees, then to go to the next state, you just see that how much I have to spend from this place to this place to this, means what is the cost, and you add that cost to the previous cost, because this was the cost you came to this point, and you add this thing so that you can put those next item with the things. So you see that for all the actions, if you find out if the child node is not explored, then you put into the frontier, and otherwise if it is also there already there, then you decrease its path. So what does it mean? It means this this thing particularly, that I'm just going to see you the frontier. Okay, just see the frontier. Okay, let's assume that this is the frontier. It contains lot of nodes. Okay. So you were somewhere here, and you find out that these four states, these four, say S1, S2, S3, S4, should be placed into the frontier. So what would you do? You see that whether this item has been already visited. Already visited means what? Already visited means it already had came into the frontier and taken out, then you are not going to consider that item. If this particular item has not been frontier any time, so you put it into the frontier. Okay, S2. How would you put? Because there were some initial node from there you were telling and reaching to this state. So you see that if let's assume that this path has incurred you the cost of 100, and this state is going to cost you 5. So you put S2 with the value 105. So what does 105 specifies? Because all these states which are into the frontier, they have the value. So using these value, you would sort and you would find out what should be the right position of this item. Are you able to see this? There would be some other states. That is an important point I am going to tell you. There would be some other states. Let's assume that if you come here from here, and let's assume the S3 is already there, and this cost is say 8. So what is the overall cost? It is 108. And let's assume that initially it is 205. S3 was there with the value 205. What would happen? S3 is the value with 205. What would happen? The algorithm says that there could be 3 conditions. Number one, when I explore the things, it has already been into the frontier and it has actually taken out from the frontier. Such items I am not going to consider because they had already visited. For those kind of items which I am seeing the first time, I would be putting that into the frontier at the right location, because if it is 105, so definitely S2 would come before the S3 somewhere here. If S3 is the item which is inside the frontier, which is there into this frontier, okay, ये तो हो सकता है either it is inside the frontier और इसमें अभी नहीं है और इसमें आके जा चुका है. Three things could be there. If it has came and gone, not considering. If it had not came, I am putting it here. If it is there, not gone, still staying, so I would see that this value is 108. I see that this value is 108 and this value is 105. So I would replace this value with the 108. So what does it mean if I replace? Replace is not just a replace. This item would also be shifted somewhere else. Okay, because its value is changed, it would be shifted. So what is the effect of this shifting? That order in which you are considering the item maybe this time is going to be different. Understand this thing? So this is overall the algorithm is how to identify the item which are taken out correct. To identify whether the item is taken out or not, I told you that what you can do, that for every state you keep Another characteristic that you can call as a color. If the color is white, you see that I am seeing this first time. If color is gray, it means that it is inside the frontier. If color is black, you say that it has been taken out, and I'm not going to consider it. So you can use another attribute as a color with every node to distinguish and find out this information. Is it clear? This is a very important point that you need to understand, that a goal test is applied to a node when it is selected for expansion. Okay, goal test is applied to a node when it is selected for the expansion. What does it mean? Goal test, it is, I think it is wrongly written. It is test. Goal test is applied to a node when it is selected for the expansion. So sometimes what may happen, that you are in a state and you go to the next state, you find out the goal state. So you are not using that state as our output. You are actually you are not giving the output until it is this particular node has been taken out and taken out for the expansion. So I would give you an example. Okay. And the same thing I'm telling, that the value of GN, that is what is the cost that you got from the root to here, is actually updated if the better path is explored. So let us see an example. So this is the same graph that we have seen, that is a subgraph of that. And Sibiu, there is a place, and Bucharest is the final destination. Let's assume that I want to come from Sibiu to the Bucharest. Okay. What are the successors for the Sibiu? Okay. There are two successors. Okay, Valkia and Fagaras. There are two places that we can go, and they have the path 99 and 80. So what would happen, that since you are putting Fagaras and Valka into the let me just take the printout, put it here and tell. Okay. So what would happen, that in your frontier initially there would be Sibiu, SIBIEU frontier, there would be only Sibiu. Then what would you do? You would take it out because to explore, and you find two things that are Fagaras and Valkia. So then you would see that Valkia is smaller, so you would be putting Valkia, WILCEA, with the value 80, and FAGARAS, Fagaras, with the value 99. Okay, then into the next step you take it to you take Valkia out. Okay, because it's a small thing. So the last node was Valkia, it is expanded, therefore you expand this. So what you can expand? So you would expand at the PTCT, so you would put it over here, PITESTI, PTST you are putting. And but what is the value? It is 97 plus 80. I told you that earlier, whatever value you have, so 80 plus 97 is 117. So you are putting 117 over here. The next item you take out from the frontier is this. This item is the next item. You got 99. Okay. So next node is Fagaras. So what you would do? You would see this and you would explore this thing. And when you are exploring this, you are finding 99 9 plus 211. You find out 99 plus 211, and the next 310 is the answer. So you put this Bucharest. You put Bucharest with value 310. And this is the important point that I want to bring in your notice, that I have put the Bucharest over here. Okay. Although it is the although I want to go to the Bucharest, so I find out the solution, but I have not tested whether it is a final state or not. This is the important difference between the DFS BFS, because DFS BFS, whenever they take the item, they test whether this item is a finalist item or not. If it is a final item, they stop. But this algorithm, uniform cost search, would not stop at this moment. It would just put this thing into the frontier. Okay, so what would happen next? Next item is, what is the next item? Because it is a 310 now. It is a 310. What would happen next? Next, I would take this 117. I would take, however, the goal node is generated, but the algorithm would go on expanding. So what is going to happen if you expand this thing? You are getting a new state again, Bucharest, and this state, the same condition that it has came and it is into the frontier. So what would happen? You try to see what is the cost. The cost up to this point is this 117. Okay, 177. The cost up to this point is 177. Okay, this is 177, and next is 101. The overall cost is 278. Okay, 278. Overall cost is 278. So you would see what is the cost over here. You see 310. So you remove this thing and put 278 over here in this line. Okay, you find out the value to be 278, and then by this its place can be changed, and then you take it out, and since it is and then you have to explore this Bucharest, and you know this Bucharest thing is the final state, because when you take this out you would test that whether it is a goal state or not. You find out, okay, this is the goal state, then what would you do? You would stop over here. You would stop over here and you would report the answer that the distance is 278 kilometers. Then you can backtrack to find out what is how you have came to this particular point. Is it clear? Can anybody tell yes? Is it clear? Is it clear? I just told you that although Bucharest was explored earlier, but we have not put that thing, we have not reported that as an answer, because after a later point of time something came and it has reduced its value, and therefore we got the better path. Okay, in general, this kind of uniform search is optimal. Optimal means what? It gives you the minimum one answer. If there is minimum answer available, then it would give the answer. Somebody is asking, please explain why we did backtrack to get 287. We have not did any backtrack. We have just forwarded this algorithm, okay, one by one. Initially, this was item, then we have taken out the second item, then third item, then fourth item, then fifth item. Every item one by one, based on their values, we are taking out. You understand this thing? And whenever I am going to get for example, when at the point when I took the Pitesti out, then at that time when I explored it, I again got the Bucharest. And when I find out the summation, what is the cost for this thing, I got 278. So whenever I get items, I told you that there could be three conditions. Either I have taken this item and this item has taken out. For example, if at the Pitesti, I would also go a part to go to Vilkia, but I would not use that part. Why? Because the color of the Vilkia has been black, because I have already seen that item, because it was came here and gone out. So there are two places that got generated, but one of them was came in and gone out from the frontier. I am not going to consider this. This is the new item that was actually, if it has been a new item. For example, earlier when the first time when you are Fegaras and you find out Bucharest, you just put into the frontier. But the next time when you see that the item is already into the frontier, you see that what is the value. You find out the value is 310, and therefore you replace that value 310 with 278. This is what we have done. So it is a progressive algorithm. Okay. There is a question when the search will stop. The search will stop when you got an item that is when you got an item that is a goal state. So when you took out the Bucharest, you would stop. When you are putting the Bucharest, you are not going to stop. When you took out the Bucharest, then you are going to stop. Okay. If all the path to the goal has been traversed, but still there are some nodes in the frontier, will we traverse that? No. Whenever the item I got a goal state, I would do the backtracking to find out how I reached over there, and then I would report that as an answer. Okay. When the search will stop? I told you, is it clear? When the search is stopped, the question is when the search would stop. Is it clear? Okay, correct. All right. So how much time this algorithm is going to take? Space and time. What is the space and time complexity of this algorithm? So this is represented by this weird formula. Let me just tell you what it is. Let's assume that C star is, let's assume, is a one value. Because we don't know what is the optimal value. Let's assume the C star is the cost of optimal solution, and if epsilon is the least cost, is at least epsilon is the is something that is at least being cost on each of the actions. Okay, on every action I at least have to pay for this. Okay. So you can say what is the minimum over here? You see the least value is 80. Okay, so here you can say that more than minimum. If you can say that epsilon is, what is the minimum? Epsilon is the least cost. So from here to here you spend 1 rupee. From here to here you spend something 99 upon 80 rupees, that is greater than 1. So you take the smallest one and you divide this by total cost. So what is the total cost? So let's assume that total cost that came out to be 287. Then you divide by 80, and you find out, you add 1 to that, because you start, at least to get the start you have to invest 1. So this is the B represent the branching factor. So although you see that somewhere the branch is 2, somewhere I think everywhere the branch is 2. From here also 2 item, 2 item. The B is 2 to the power 1. It is 287 divided by 80. So this is what the complexity is. Okay, you understand this formula? Okay, somebody is writing hi sir, please write questions. Okay, somebody writing hi sir, please write whatever is in your mind, you can ask the question. So is it clear? Am I clear at this particular moment? Okay. So I am telling that at every place you see that how many items are going, that is B. Okay, earlier also I also told you B means branching factor. Branching factor. Okay, branching factor. So then you apply this formula, 1 plus C is the optimal cost divided by the minimum cost. Then this is the formula that gives you the space and time complexity for this thing. Is it clear? Okay. Okay, so next, what is the important difference between the previous algorithm, means DFS and BFS, and this uniform search? The difference was that the goal test is applied to the node when it is selected for the expansion, and they were applying whenever the item you get, you apply whether it is a goal or not, and you say that okay, I am done. But here you are telling that no, I am not done, I would put this into the test. In between it may be possible that there could be some other things, some other paths are available, and they can give me the smaller thing. Okay. The question, there is some question in terms of the thinking how to approach this concept differently from graph theory, digital algorithm, etc. So yes, definitely I am telling you that digital algorithm and all other algorithms we are going to talk, because DFS is also there into the places, but here we would be seeing some different algorithm also that are heuristic based, and our target is to understand the heuristic based things, and before that we want to cover some of the basic other algorithms. So you understand what is the uniform cost search? Are you with me? The difference is this. Okay, so next thing, going to next slide. So this we have studied, and next thing is a depth limited search, and that is straightforward. In the DFS you find out what is the problem with the DFS, and the DFS has a problem, very big problem, that let's assume that your sometime it happens that your search space is very large. Okay, so if your search space is very large, your things are such that they can go infinitely deep, because sometimes many other time whenever you are going to do the searching, for example if it is a game of say chess, so it is 2 to the power 64. Such is a very large number. These many number of particles we do not have. Very large number. So if these many number of states are there, and if you are into some board position, what are the states? They are board positions. So if you are into some board position and you want to find out how to go from this place to this place, that is a winning place. So it is very difficult for you to go ahead. Okay, because if you start doing one by one, you going infinitely, you would take infinite many time to just go for one place to another, to just finish one one deep place. So therefore you would be stuck, you would not be able to solve the problem. So the first solution to this is this, that you say that my algorithm would not explore more than L number of length. So if whenever it starts from some place, it would only go L length deep. Okay, or from the root node it would not go beyond the L deep. Okay, from the root node, sorry, I'm sorry for that. From the root node it would not go beyond the L deep. So this is a modification into the DFS, and this DFS is called the depth limit search. So are you with me? Are you understand? Do you understand why we have applied this particular thing, depth limit search? Why we have modified the DFS in such a way so that you don't go all the way down and you stop somewhere. This we have done because into the machine learning, into the artificial intelligence area, so many of the time our state space is infinite. If you start going infinitely, so it may be possible that things go very bad because you have infinite length available. So you may not be able to come back. Only one side you are going to keep going, because infinite is something that you cannot come back, you cannot stop. Infinite is some concept that tells that there is no end. So you cannot go ahead. You understand this thing? So we are going to take a 5-minute break over here, and what is the time right now? It is 7:55. We'll be connecting in 5 minutes. Just keep thinking about this particular problem, and this slide is with you, and we will continue after the 5-minute break. Is it right? And please be ready with the questions if you have any. Okay, I'm going to stop.